Hello, everyone. What I want to do is finish up this chapter by talking about the open mapping theorem, and I'll talk about its immediate corollary, the inverse mapping theorem. All right, so, and I'll do one more video on the closed graph theorem and some of its applications. The closed graph theorem is particularly extremely useful when you study holomorphic spaces of holomorphic functions, as we'll see. Really, just in general, in concrete spaces of functions, really, closed graph theorem is really just invaluable. So certainly useful in PDE also. All right, so the open mapping theorem is the following. So just abbreviate this OMT. Okay, so let's say T is a bounded linear map from one Banach space to another. So both of these have to be Banach spaces. And let's say this is onto. So the claim is that G open implies that T of G is open in Y. Okay. And this is really, if you remember, putting this in terms of topology, this is extremely important and useful. And we absolutely need both X and Y to be Banach spaces. As you'll see in the proof in this video, we need Y to be a Banach space so that we can use bare category theorem. And we're going to use the fact that X is a Banach space directly. We're basically going to construct a nice Cauchy sequence, and we need to know that it converges. Well, we're in a Banach space, it does. Okay, so as a consequence of this, we get the inverse, sometimes called the inverse mapping theorem. And this is just an invaluable result. So if we have a bounded linear map between two Banach spaces, and again, X and Y are Banach spaces, so this is a bijection. Well, we know, or should be able to prove very easily, that the inverse map is linear, so that's not in doubt. What might be in doubt is whether or not the inverse is bounded. A priori, there's no reason to think it would be bounded. Well, this open mapping theorem essentially says that the inverse map from Y to X is actually a bounded linear map from Y to X. Yeah, so what's the proof? Well, this is, you basically probably proved this in advanced linear algebra, that if you have a bijection between two linear spaces, the inverse is also linear. Nothing to that. Right. However, we proved that any linear map is bounded between two norm vector spaces if and only if it's continuous. Okay, and so this is one of those times where the abstract topological definition of continuity is extremely useful. This is, sorry, if and only if this is continuous. This is true if and only if this following statement is true. Well, continuity is equivalent to the inverse image of an open set is open. Well, take something in X. I'll just write it like this. So G open implies the inverse image which of course is just T of G is open. So continuity is equivalent to T of G open whenever G is open. Well, this is true assuming this open mapping theorem. Right. So really this is, as I said, in the next video, we'll talk about the closed graph theorem. I don't remember if I said this, but in the next video, we'll talk about the closed graph theorem and discuss some applications of that. But really, the main direct application of the open mapping theorem is just this invaluable fact that you don't have to check that the inverse is bounded; it's automatically bounded. Okay, so yeah, the proof of the open mapping theorem is tricky, but there's some really beautiful parts of it that I think are useful to keep in the back of your head when you go along and do your own research and kind of whip out your toolbox of proof ideas and techniques. So that's why. So I'll present it. So the key to the open mapping theorem is what the book calls Theorem 318. So first, before I state a theorem, let's just get some definitions out of the way. B of y, B for ball here, is, well, it's just the open unit ball centered at 0, which is, as you would expect, set of all y with norm less than 1. Okay. And for delta positive, delta by is going to be, well, just multiply everything in by by delta. And that's pretty trivially just going to be the ball, open ball, radius delta, center 0. This captures all basically y delta time. Well, I mean, just trivially, this is going to be the following. I hope there's no doubts. If there is, just prove one's a subset of the other, basically. Okay, so the key to proving the open mapping theorem is the following theorem. This is Theorem 318 in the book. Yeah, and this theorem says that there exists positive delta where delta times a ball of delta times this ball here, well, really the ball of radius delta center 0 is a subset of T of the unit ball in X. The image of the unit ball in X under T. And the unit ball in X is, well, same thing as this here. Just replace big Y with big X. Right? Okay, so what does this really tell us? Well, what this is really telling me is that, and this is really what's important. If y is less than delta, then y is in the image of the unit ball of x. So y equals tx for some x norm less than 1. Okay. So let me do a little reformulation of this that's kind of trivial using linearity. So this is what I need to prove. That if the norm of y is less than delta, then y is tx for some x with norm 1. Y is in big Y, x is in big X. All right. So let's see how this proves the open mapping theorem. Okay. So let's pick x0 and g. So what am I going to do? I need to find a neighborhood around t of x that's contained in t of g. That's going to prove that t of g is open. We're picking an arbitrary point in t of g. That's just tx0 for some x0 and g. So we need to find a neighborhood about this arbitrary point in tg that's a subset of tg. That'll prove that tg is open. Right? All right, so yeah, and this is going to be fairly easy with using linearity. So let's consider g. So we just got to reduce, basically translate. That's kind of what we're doing. Just translate things to the origin. Basically move g kind of to the origin. What do I mean by that? Well, let's look at g minus x0, which is just all x minus x0, where x is in g. Okay, right. So this is certainly open because we're assuming g is open. And certainly, well, x0 is in g. So x0 minus x0 is in g minus x0. So 0 is in g minus x0. So we can pick a small ball, with center 0, radius t, that's contained in g minus x0. So it's open. We translate an open set, it's still open. Right. So let's do that. Pick t. I'm going to try and keep the same notation as the book. The book, for some reason, goes from a bounded linear operator being bounded linear map being from t to a. I don't know why they picked t and then moved to a. I'm going to just use big T throughout. Otherwise, it's just weird. But anyway, yeah. So and yeah, just remember, this here is just all set of all x and big X, where the norm of x is less than t. It's just the ball of radius t, center 0. Okay. So by this theorem, we're assuming theorem 318 is true, theorem 318. So we can pick delta bigger than 0, where delta times the ball of times this ball here is a subset of the image of the unit ball, center 0, at x. So particularly when this notation here, so clearly this is a little more transparent, I guess, than this formulation. But when actually using linearity, this is probably a little clearer or a little easier to use. Okay, so I claim we're basically done. Why? Well, we can use linearity, and if any of this looks funky, definitely check it. So by linearity, let's multiply both sides by t. Really, really dilating both sets by t, but. So this is a subset of t, big T, x. Well, by linearity, this is just, again, check this if you have any doubts. Probably shouldn't, because it's just dilation, and you can pull out constants from t. Well, t bx is a subset of g minus x0. So t of t, little t bx is a subset of g minus x0. And this is going to be equal to, again, by linearity, tg minus t of x0. So what have we proven? Well, we're done. Just translate translate these two sets here by big T of x0. We get t delta by is a subset, this plus x0 is a subset of tg. Well, this you can check is most certainly a neighborhood of t of x0. Okay. This is an open set. You're taking an open set and translating it. Okay. So we found an open, a neighborhood of tx0 contained in tg. So we're done. Okay. Right. So, all right. So let's reformulate this a tiny bit. This star here. So I'm going to make a little claim here. So to prove star is enough to show what I'm going to call star star, there exists D positive where if little y is in big Y, then little y is Tx for some x less than 1 over d times the norm of y. Okay, and this is just a really kind of trivial reformulation, but it's extremely useful for us because you can iterate this, as we'll see in a moment. So I'm going to call this star star. Well, let's assume star star is true. So what do? We need to pick, we need to find some delta where this is true. And I claim delta is just D. Delta is little d. Well, then y equals Tx. I mean, maybe to make this, I mean, not that there should be any doubts, but so we're saying y equals Tx for some x, little x and big X, where this is true. Well, obviously this is going to have norm less than 1. That's exactly what we need to prove. That's exactly what we needed. We needed the norm of x to be less than 1. Okay, so again, pretty trivial yet extremely useful. Okay. So we're going to prove this in 2 stages. The first stage is to basically get an approximation kind of result of this that almost kind of gets ever so close to proving this, but not quite. And this is a really nice proof strategy, particularly, you know, like if you want to basically think of like a partial differential operator, you know, acting on you know, a function, and you want to, let's say that's, I don't know, give that partial differential operator a name, L. You know, you want to say LF equals a given big F. You know, you kind of approximate a solution and then take limits to get an actual solution to your PDE. This is no different at all. So we first prove an approximation kind of version of this, this here that we need to prove. Okay. So, and this is lemma 319 in the book. Okay, so there exists D where if y, so we're starting off exactly here. There exists D where if y is in big Y and epsilon is bigger than 0. And I want to emphasize D is independent of little y and epsilon, completely independent of little y and epsilon. So I claim there exists big X satisfying the same bound here. X less than d minus 1 form of y. But we don't quite get y equals tx. We get y minus tx is less than epsilon. Okay. Okay, so, you might think, well, okay, what would be a good proof strategy then for this here? Well, you could just say, so really x depends on epsilon, so you could just say, well, here's x epsilon, or better yet, let's take epsilon to be 1 over n, so we get what would we get? I'll write that back in a second. You get xn. Well, the problem with this is, this will be, 1 over n. You don't really have any compactness in a general Banach space. If you have a reflexive Banach space, then you certainly have the unit, any bounded set in a reflexive Banach space, has if you have any bounded sequence in a reflexive Banach space, you can use what we proved, the Banach-Leoglu theorem, that that's going to have a convergent subsequence. Well, we don't know that X is reflexive or not. So we have to be a little more clever is all I'm saying. So you really just can't use any kind of compactness. You can't use any kind of Bolzano-Weierstrass theorem for big X because there is none for just an arbitrary Banach space. But still, we're going to kind of cleverly get around that, as we'll see in a moment. Okay, right, so let me prove this. Right. Now, proof is actually pretty easy. It's just a, so I want to make clear that my running assumption is that T is onto. Okay. So this is where I'm going to use T as onto. That's my assumption for all these results here. Okay. So in case it's not clear, T is onto. And the fact that T is onto allows us to use a bare category theorem in a pretty not super subtle way. Well, T is onto, so trivially Y is Tx. Really not anything more to say than that, it's just a definition. And I can write X as just the union of balls center 0, radius K, as K goes from 1 to infinity. And it seems kind of maybe a little silly, but well, maybe it's not so silly because, whenever you can write a Banach space as a countable union, you can use their category theorem. And particularly, you can exploit linearity to get what you want. Now, of course, just 299 stuff, you can pull out the union from, T of the image of a union is the union of the image. K, X. So the only annoying thing, though, with bare category theorem, I remember Y is a Banach space, so there's no problem there. But all bare category theorem says is that a complete metric space cannot be written as the well, it says that it can't be written as the union of nowhere dense sets. So that means one of these sets has to have the closure has to have a non-empty interior, and that's kind of a pain that we can only get the closure, but yeah, that's basically all we can do. And that's kind of why we're proving an approximation version of this. Okay. So by the bare category theorem, for some k, some integer k, where this closure here, t, kbx, has non-empty interior. Okay, so so there exists well, a ball with center y0, lack of anything better to call it, r bigger than 0. For this ball, center y0, radius r, is a subset of this closure here. Right. Right. So, what does this tell me? Okay. Well, if I have any y tilde, for lack of anything better to call it, in big Y with norm less than r, then y0 plus y tilde. So this is kind of my let's exploit linearity trick. Okay. Well, this is trivially true. Take the norm of this y0 plus y tilde minus y0 that has norm less than r, because y tilde has norm less than r. So that means this here is a subset of the closure of t, k, bx. Now let's just use definition of thing in the closure. So we have this here. And we have, we'll kind of emphasize something here. Certainly y0 is the center of your ball is in the ball. Okay. So we have y0 is in this closure. We have y0 plus y tilde is in this closure. Okay. So we can pick sequences xn prime using the book's notation, xn second prime, in kbx, where t xn prime converges to y0 and big Y. So again, y0 is in the closure of tkbx. So yeah, pick something in tk be x that approaches y0. Okay. Do the same thing for y0 plus y tilde. So t of x and second prime converges to y0 plus y tilde. Okay. All right. Right. So right. So all right. So let's continue on here. So what does this mean? This means that well, as n goes to infinity, this here by linearity, well, it's pretty obvious what this is going to converge to. This is going to converge to y0 plus y tilde minus y0 equals y tilde. And notice that take the norm here. This is less than or equal to the norm of x and prime. Just triangle equality says this is going to be less than 2k. 2k because both have norm less than k. Okay. All right, so what have we proved? And I think it's worthwhile to just write down what we've just proved. For any y tilde with norm less than r, remember r came from the bare category theorem. Particularly, this has non-empty interior. This is where the r comes from. So if this has norm less than r, and if epsilon is bigger than 0, then there exists x, and big X particularly. Just take x to be xn second prime minus xn prime for n large enough. Each one of these has less than 2k. And for n large enough, we can set y tilde minus t of this to be as small as we want. Okay. So we're almost done here. We just need to do a little easy linearity trick. Okay. This is what we have just proved as a basic corollary to the bare category theorem. Okay. Okay, so finally, well, let's assume y is not 0. If y is 0, then well, you just set x to be 0. Yeah, if y is 0, well, maybe I should just specify yeah, I should probably just specify y is assumed to not be 0. Anyway. Okay. Yeah, so if we pick y to be not 0, I mean, if y is 0, this is kind of, you know, yeah, if y is 0, this is really trivial. I mean, you can pick x with norm 0, just pick x to be 0, where 0 is t of 0, so certainly this is true. We don't quite get this is true, but we don't care because you can't get a norm smaller than 0. So this is really just silly with y equals 0. So, all right. So if we have a y not equals 0, so big Y, then basically just take r over 2, y over norm of y. Nothing special about 1/2 here. Anything smaller than 1 works. This is 1r. This is equal to r over 2, which is less than r. So let's replace epsilon with r epsilon over 2 times the norm of y. Epsilon is allowed to be anything I damn well please. So there exists x tilde from what we just proved. Not quite the x I want, but there exists an x where this is true. Well, x tilde is less than 2k. But again, I'm going to use epsilon, r epsilon over 2 norm of y. So I'm applying it. Yeah, this is my y tilde here. This whole thing. So it's going to be r over 2, y over norm y, minus tx tilde. Okay. So I don't feel like doing another line, but what I could just simply do here is just multiply everything by 2 norm of y divided by r. So if I do that, I guess I will write everything. Yeah, again, so what does that mean? That means y minus t of 2 norm of y over r x tilde. And I'm going to call this is what I want to be x, this whole thing here. Just circle it. This is going to be, well, less than epsilon. And last but not least, norm of x is 2 norm of y over r times the norm of x tilde. Norm of x tilde is less than 2k, so this is less than 4k over r, norm of y. So all we do is set d to be r over 4k. And you'll notice that d is completely and utterly independent of epsilon and y. What does d depend on? Well, it depends on r and k. What does r depend on? What does k depend on? Well, we're just using bare category theorem. So it just depends on my two Banach spaces, x and y, and t. Okay? That's it. It just depends on t, big X, and big Y. K and R just come from Baire category theorem. Has nothing to do with little y, nothing to do with epsilon. It just comes from the Baire category theorem, so it depends on big X, big Y, and T. Okay, so we have this lemma here. Now let's prove this star star here. Let's see how to cleverly iterate this approximate version of star star to get what we want. Right. Sorry, using lemma 319. And I definitely, you do solve PDEs and non-reflexive Banach spaces. I can almost guarantee that Professor Bachanu, I can't really ask him at the moment, but I'm almost 100% sure even Professor Bachanu does PDE theory in non-reflexive Banach spaces. So this kind of iteration scheme is quite interesting. It's quite useful. Probably have to be a little more clever when you don't have linearity, but anyway. Okay, right. Yeah. Okay, right. So we're going to basically use lemma 319 iteratively. So step one is going to be as follows. Right. So as we'll see, decisively, we're going to use linearity. So I'd be curious if there's any way to salvage this iteration scheme and this kind of technique when you do not have linearity. Though there's various degrees of linearity in PDE, like quasi-linear, and there's, anyway. All right, so step one. So actually, before I do this, I want to use the book's notation here, because I think it's extremely useful. This epsilon here is going to be my tolerance. It's kind of how close I want y and tx to be. So I'm going to call this my tolerance. And y is going to be my target. The idea being, I want to pick an x where tx is y. That's kind of my target. I'm aiming for y. I don't quite get there, but I get there within a tolerance that I'm okay with. Right? And that tolerance is epsilon. Okay. Okay, so pick x 1 with x1 less than d to the minus 1. So actually, so first, let me make an assumption here. let's assume the norm of y equals 1. And I'll get back to how to do it in general. Actually, I'll make that probably for homework. Okay. So in, whoops, sorry about that. So in this here, I'm going to assume y has norm 1. Proving it in general is fairly straightforward. Okay. Right. So pick x1 with the norm of x1 less than d. So my actual y is going to be my target for my first step. So in using lemma 319, this is my tolerance for step 1. And this is my target. Right. Okay. All right, so let's do step 2. All right, step 2 is pick x2. And I should say, really, it's, well, really, lemma 319 just gives me this here. Well, y we're assuming has norm 1. So this equals, squeeze it in here. This equals, well, d to the minus 1, because y has norm 1. Okay. Now I want to pick x2. So maybe I should just say, because I'll do it here, y is my target, but I'm going to specify my target beforehand. Cleaner, neater. All right, so pick x2, where the norm of x2 is less than d to the minus 1 times the norm of my target. Now I want my target to be this whole thing here. I'm allowed to pick my target to be anything I want. So this is my new target. Okay. Right, so this here, and the beauty here is that you can basically whatever you get inside the norm, if you keep setting that to be your new target, you have a nice bound for the norm of the x that you pick. In particular, this is less than 1/2. So this is going to be, sorry, I don't want it 1/2, I want it d over 2. I can pick my tolerance to be anything I want. I want it to be d over 2. So that doesn't really matter all that much. But for consistency, it makes it a little cleaner. So this is going to be d to minus 1, d over 2. And this is what the book does. So that's 1/2. So I haven't specified my new tolerance that I want, and I can pick it, as I said, be as small as I damn well please. So sorry, it's my target, y minus tx1 minus tx2 I want this to be less than d over 2 squared. So this is my new tolerance. And just to remind you, this is my target. Okay, so I'm running out of space here. Zoom Blackboard. Okay, so you just keep basically iterating this. So, or do this inductively. So in general, for given x1 through xn, I just did the case n equals 2, where the norm of xk is less than 1 over 2 to the k minus 1. And we just, we did n equals 1 and 2, really. Well, so I guess well, norm of x1 is d to the minus 1, so it doesn't really work for k equal 1, but to n, we don't really care about k equals 1. And y minus, well, basically like this here, but keep going. Y minus tx1 minus dot 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 minus txn is less than d over 2 to the n. Okay, so we do what we've basically been doing. This whole thing here that I'm going to circle is going to be my new target. Just like this was my new target. Right? So we pick xn plus 1. Where the norm of xn plus 1 is less than or equal to d to the minus 1 times the norm of my target, which is exactly this here. Okay, so again, this is my target here. Okay, so it's going to be it's going to be my target minus t of xn plus 1. I'll put my target in parentheses. So it's really not that hard of a proof. It's more clever, I think, than complicated. Just we're all on the same page here. And I want my tolerance to just match the induction. So I want it to be d over 2 to the n plus 1. And of course, this is by lemma 319. I've been implicitly using that here. Here. And here. Okay, right, so we're almost done. Okay. So it's kind of maybe clear what we do now, really. y minus this whole thing here is obviously small, so we kind of just want to take limits. We just want to hope that, and obviously I should say this whole thing here by linearity is going to be, maybe I'll do this whole thing here is minus t of x1 plus xn. I mean, it's absolutely trivial. There's nothing to that. Just use linearity. So if we can get that x1 plus dot 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 plus xn converges as n goes to infinity, we can take limits and use continuity, and we're kind of trivially done. Well, we can, and this is where we need x is a Banach space. So yeah, I want to emphasize we're basically done. The rest is pretty easy. So a Vn, just using the book's notation, is not subtly from what I just mentioned, x1 all the way to xn. And I claim this is Cauchy. And that's really pretty easy. What's the proof? The proof is if n is bigger than m, well, this is going to be equal to the norm of the sum here. K equals m plus 1 to n. I'm writing it like this because I'm running out of room here. We'll use triangle inequality. And we'll have to use triangle inequality, just replace n with infinity, adding more non-negative terms. So kind of trivial. So this is going to be less than n plus 1 to infinity. 2 to the minus 1 over 2 to the k. I think it's k minus 1, which is it? It's k minus 1. Norm of xk is less than 1 over 2 to the k minus 1. And that's going to be, just pull out the 2 to the m. You're going to get this is going to be equal to 2 to the minus m plus 1. And that proves the claim. That's as long as n is bigger than m, this here is less than 2 to the minus m plus 1. Okay. So finally, let x be this limit here. So like I said, it's basically trivial that because of this, if x1 plus dot 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 plus xn converges as n goes to infinity, then t of x is going to be equal to y. Well, let's just write that easy proof down. Okay. Well, tx by continuity is t of x n. This is going to be the limit of Vn, sorry. And by linearity, Well, this is trivial. Because this is less than, what do we say, delta d over 2 to the n. Right. So as n goes to infinity, yeah, we're done. Okay, so that takes care of that. Finally, the norm of x is just use triangle inequality. The norm of x is less than or equal to the norm of this infinite sum, x1 through xn as n goes to infinity. So just collapse in the norm using the triangle inequality. It's less than or equal to the sum here, trivially. And this is less than d to the minus 1 plus, well, x1 has norm d to the minus 1. The rest has norm less than 1 over 2 to the k minus 1. Yeah. So it's going to be d minus 1 plus 1. So we have to modify d a tiny bit from lemma 319 to star star. We have to add 1 to it, not a big deal. Okay. So what have we proved? We've proved that given any y with norm 1, there exists an x where y equals tx. Maybe it's a bad color. Use the purple here, I guess. Yeah, given any y, given any y with norm 1, there exists an x where y is tx, and the norm of x is less than or equal to d to the minus 1 plus 1, which is just kind of like my new d to the minus 1, essentially, times the norm of y. Right, so yeah, so as long as y has norm 1 with the slightly different d, we're done. This is exactly what we need to prove. So I'll leave it for homework to prove this in general, to eliminate the assumption that y has norm 1, as I mentioned before. And it's really a very easy play around with linearity. Okay, so again, this is a long proof, long video, but I really, really like this kind of iterative scheme. I just like this proof technique a lot. Basically, going from an approximate version of what you want, lemma 319, iterating this to actually get what you really need, this result here. Okay, so as I said, next video will be on the closed graph theorem, and I'll do some applications of the closed graph theorem. So like the book, I'll do some applications to the Bergman space, talk about composition operators, or at least for the homework, I'll talk about composition operators in the homework rather. And in the next video, we'll look at putting different norms on the Bergman space of the unit disk, and we'll see those norms are basically the same. I'll be given to us by the closed graph theorem. That's a result that I've used in my research. You often have to take a holomorphic function space and just put a norm that's different but more convenient for whatever you're doing. All right. So long. Take care. Bye-bye.